starting for this tutorial. We didn't do any questions yet, but we will start very soon. So I'm going to bring up the 2019 exam. And I believe the questions wanted me to do the multiple choice ones. Yes, multiple choice. Exam 2019 multiple choice A. So I think actually I can bring this up. Yeah, look at this. Okay. So what I can actually do is, no, I can't actually. Okay. I tried. Naomi says, we will not cover the sulfonate ester mechanism in the exam. Does that include everything? No, just the mechanism. You still need to know the reactions, Naomi, and you still need to be able to use them in reaction schemes and all of that. You just won't be asked to draw the mechanism out. And that's because we didn't cover it in my section, and we found that out only when we were putting the exam together. All right. So the questions that I was asked for on the 2019 exam were 5, 7, 16, and 42. And question 5 gives the following compound. That looked terrible. Okay. We have all right, you have this molecule, and we are reacting it with HBr, and we are asked what the major product is going to be, and it gives 5 answers. So what's going to happen here is you're going to start with a proton transfer. I can just draw like that. OH2 plus. And once that's protonated, it'll come off to make a carbocation that is secondary. All right. Now, what can happen in this situation, because this is a secondary carbocation, is you can have a rearrangement. And to do the rearrangement, there's sort of 2 ways we could do it. One is we could shift the methyl group over. The other is we could do a ring expansion. Okay, so both of these are possibilities. If you consider both, do the methyl shift first. You're going to end up with this cation, which if you have Br, actually make it blue. If you have bromide, what it can do is then attack where the carbocation was to give this compound, which that's answer B. But if you did the other way, what happens is you do a ring expansion where you end up making, so I'm going to show you exactly how we're going to do this. First, what we're going to do is we're going to label all of our carbons. We're going to go 1, 2, 3, 4, 5, 6, 7. Okay, and what we're doing is we're breaking our 1,4 bond and making a 6,4 bond. Okay, so 1, 2, 3, 4, 6. So we're going to have pencil. So carbon 1 still there. 2, 3, 4, and 6 is the new bond that formed. Well, 1, 6 is already formed. 4, 6, that's the new bond right there. we still have carbon 5 attached to carbon 1, and we still have carbon 7 attached to carbon 6. 5, 7. And the positive charge will go on the position where the bond broke. So the bond broke from carbon 1. Positive charge there. Now we have Br minus. This can attack the cation, and you get Br. So this is a tough one. This answer here, by the way, it has, I mean, that's answer E. There will be more than one stereoisomer of this possible because we have 2 chiral centers. So I guess that means there's a total of 4 possible products, but we're only going to draw, only one of them is included. I would say that the best answer here is E. And the reason why that's better is because by doing the ring opening that way, you're relieving the ring strain. You're ending up with a more stable ring, and that would lead to a more stable compound. So I'm not looking at the solutions right now, but I'm guessing the answer is E. Can someone confirm that that's the case in the answers? All right, the next one people wanted to see was question 7. Question 7. That was a nasty question, actually. What's Avery saying here? Is it because of the angle strain? Yes. It's better to relieve that angle strain rather than pick the one where you do not relieve the angle strain. Which of the following represent a set of constitutional isomers? So we're given this, 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 and this. So I mean, the first thing that we could probably do here is come up with the molecular formula for each of these. So this one is going to be C4H8. This one is C4H8. This one, C4H1, 2, 3, 4, 5, 6. This one is C5, 1, 2, 3, 4, 5. H, 1, 2, 3, 4, 5, 6, 7, 8. And the last one over here on the right is C4, H, 1, 2, 3, 4, 5, 6. So this is an interesting one. I would say that these two are constitutional isomers, and these two are also a set of constitutional isomers. But they are not, you know, there's 2 separate sets of constitutional isomers. So what's the answer? I would guess either 2 and 5, or I would also say 3 and 4. I think the answer was only one of the sets, which may have been confusing. Okay, well, there we go. So the answer is both. Probably, I guess, if you're picking an answer, are any of the correct answers on there? Yeah, D is correct. I guess D is the answer because the other set doesn't appear anywhere, but the other set is also a set of constitutional isomers. So yeah. So 2 and 5 definitely are a set, and that is a correct answer. The other set, which are also constitutional isomers, don't appear as an option. So I guess from the perspective of choose the best answer, that is definitely the best answer. All of the other ones are wrong. That one is correct. It just happens there's another correct option that isn't one of the answers. As far as I know, we don't have any questions like that on this exam, unless we made a mistake, but we've each checked it twice. We made a list and checked it twice. Question 16. Question 16. Which reactions would yield a meso? This 2-butene H2Ni, same molecule, Br2. The next one is osmium tetroxide with the rest of its conditions. C. Formatting here is kind of screwed up. Okay, that's ABC. A, B, C. D is the trans with K, MnO4, cold, and E is more than one of the above. So let's just draw out the products we're going to get for each case. The first one is a hydrogenation of an alkene, which gives you that, which has no chiral centers, which is not meso. The second one will add Br2. The addition of Br2 is anti. So that will give you as a product, plus it's an enantiomer. This is not meso because there's no mirror plane that runs through it, right? It's not a reflection plane right there. There are chiral centers, but this will be a chiral molecule. C is osmium tetroxide. That does syn dihydroxylation. So that would give you this product. That one is indeed meso. Meso. Because it has two chiral centers and a mirror plane. KMnO4 cold does the same reaction as osmium tetroxide, but we're starting with the trans isomer in this case. So what this is going to do, if you can imagine having the alkene flat like this, where we have the hydrogens out here, we're going to add one OH up here, one OH down here, which is going to end up giving us this product. Or another way of drawing that, if you rotate that around a little bit, is so that's not meso. It's got chiral centers, but no mirror plane. So this reaction, you know, if you start with a cis alkene and you do syn addition, you're going to get a meso compound like you see in this case. But if you start with the trans molecule and do syn addition, you are not going to get a meso compound. But if you started with this and did like Br2 in a nonpolar solvent like hexanes or carpentet, that will add anti. So adding anti to a trans alkene will give you a meso compound. So the answer is C, as the only conditions here that are going to give you a meso compound. I saw a comment pop up from Lizzie. Still confused what makes the mechanism syn. Could you please explain what that means? KMnO4 cold does add syn, yes. Syn means that both of the things that are added, something's being added to each carbon in the alkene, both are added on the same face of the alkene. So an example would be if you have an alkene where this is coming towards us. Is that a pretty terrible drawing? Do you know what I'm getting at here? This is like a cyclohexene. Maybe I could do a better job. Carbon there. This is flat, so like, you know, this is the top, this is the bottom. Think of it as like a horizontal, you know, it's not perfectly flat, you know, because it's It's a bit of a chair structure there, but what it means is the things we're adding both come from either, if they both come from the top or both come from the bottom, we say the addition is syn. If one comes from the top and one comes from the bottom, we say it's anti. So Br2 is anti. If you reacted that with Br2, you would end up with something like with a Br up there and a Br down there, the other positions being hydrogens. Whereas if you added syn, it wouldn't matter if they were hashed or and wedged. Right, so I've kind of drawn it, you know, with that perspective. But if you draw it like we normally draw it, which is this, and you did syn addition of, I don't know, like if you do the osmium tetroxide reaction with all the other conditions there, which if you're asked to draw conditions, draw everything, you would see both OHs add on to the same face, like that. So there'd be cis, or the, you know, in the product. This would be syn addition. Cool. 1642 is the last one. We're going to skip ahead to 42. Let me find it. What would the major product be of the following reaction? Okay, look at this good one. This is a reaction that people always forget about. We learn it really early on. It's maybe one of the first reactions you do. What this does is it will convert the molecule into an alkoxide. What you end up with is O minus, K plus, and H2, which I guess you get half a mole of H2. This is one of the standard ways that we make alkoxides. We use either potassium or lithium or sodium. They're all group 1 metals. They all basically do the same thing. Sydney asks, so that's basically something we have to memorize. Memorize what? I'm not sure what the question was.
I was referring to the syn slash anti, the way that certain things add in different reactions.
So luckily, I would say yes. And every other year, you'd have to memorize that. But this year, since it's open book, you can just have it ready. Yeah. There's a summary at the end of each chapter, I think in both mine and Terry's slides, which go through each reaction and summarize whether it's syn or anti or neither, because many reactions are neither, right? That sometimes, you know, there's no preference, for example, for it to be syn or anti. Both could happen. That's actually a really nice thing about this course in particular, being open book. There's lots of little small details that you don't have to spend any time trying to memorize them, because you can always just find them. And what I always used to tell people was, you know, I don't want people to spend a lot of time memorizing conditions, like is it sodium borohydride or is it, you know, whatever, as the extra reagents. And I tell them to look around because probably the reagents will be somewhere else on the exam. But now I can go even a step further. Just look in your notes. They're there, everything. Also, I like to point to on the, I'm going to tell you exactly what it's called, on the Acorn page. This has been up for a long time. Tutorials and review materials under tutorial PDFs. There's one called Mechanisms 3 Addition Reactions, and there's one called Mechanisms 4 Chapter 10 and 11 Reactions, which is actually misnamed. It's Chapter 9 and 10. That's a summary of all of the reactions we did in the lab, everything since the midterm, and it talks about whether they're syn or anti. It goes through the mechanism. It goes through the Markovnikov, anti-Markovnikov, all that kind of stuff. It's all summarized in those documents. If you want a nice, succinct, put together summary of all the reactions that we covered. Can I do question 4 from the written portion of the 2019 final? Sure thing, Aaron. Let me find it. Okay, old tests and exams. Final 2019 written. All right, question 4. This one. This is the one where we give you a reaction and we ask you to, we give you like a reaction, PBr3, HBr, either with a Br. And you have to pick which conditions HBr or HBr would be best, or if it doesn't matter, pick either. And so our examples are that one. OH. That would have methyl there, Br. OH, this one's got a rearrangement. Br, and then, is it the last one? OH, Br. And I know right away that there's going to be an inconsistency in one of these compared to how we're teaching it this year. And that's because they're, don't worry, we're teaching it correct this year. So here's the answers that I would expect for this particular question. The first reaction, the primary alcohol reacting with PBr3 or HBr, both of those would work. Correct answer here is either. And I know in the solutions it says PBr3 is better. This is because of a slight change in focus. And it's because I think last year she spent more time talking about if you're doing this reaction in the lab, which would be a better choice to use in the lab. And PBr3 has, for certain reasons, it's a little bit easier to handle. So it's a better reagent from that perspective. But in terms of doing the transformation, both of them work great. And so we didn't really talk about that this year. So if you get that same question this year, the answer is either. Chemically speaking, both of those work very well to give you that desired transformation. We're not considering handling and these other sort of factors, which I think were more stressed last year when we actually had you guys in the lab. The next one, though, is a molecule. So it's undergoing bromination, but there's inversion here, right? An inversion is a feature of PBr3. HBr does not do inversion. HBr, in this example, is going to do SN1, which is going to give you a carbocation. Carbocations are not specific for which way then the nucleophile comes in. So you'd get a racemic mixture if you used, well, you wouldn't get a racemic mixture. You would have 50-50 mix of that chiral center being R or S. When I say it's not racemic, it's because you have another chiral center over here, which gives you diastereomers, and it's a little bit more ugly than that. So PBr3 is the reaction you want to do for this step because you get inversion only. The next one, you see there's a rearrangement. Rearrangements only happen if you have carbocations, and carbocations only happen when you have HBr. So HBr is the correct answer for this one because that will give you a rearrangement in that place. The next one, either. There's no chiral centers, so we don't have to worry about whether it's inversion or not. There's no rearrangements possible in this particular example, so we don't have to worry about the carbocation mechanism. So really, either reagent will do this transformation just fine. Elliot asks, could you go over the difference SN1 can't happen at a primary chiral center? So why is HBr a possible answer for the first? Because in the first example, it does not do SN1, it does SN2. So the mechanism for that first one with HBr looks like this. Get proton transfer, OH2 plus. This is a CH3, by the way. And you have Br minus. And it attacks there, and you get CH3Br via an SN2 reaction. You're right, though. You can't get SN1s at primary carbons. Lizzie says, can we see the ring addition problem where it's like cyclohexane and cyclopentane? Ring addition. Ring expansion? Okay, Elliot, I'm going to go back to Elliot's question, which has 5 likes and a love. Could you go over the differences in HBr, PBr3, and Br2 and the uses of light, water, heat, etc.? Yes, a lot of very similar types of conditions that we see in this case. So the first thing we need to figure out is, are we starting with an alkene or are we starting with an alcohol? Because depending on which one you start with, you're going to get 2 different sets of conditions. So let's limit ourselves at the beginning with alcohols. So with alcohols, there's no reaction of alcohols Br2, no reaction. This isn't, we don't use Br2 to do anything to alcohols. We use HBr and we use PBr3. So an alcohol, I'm going to pick this one here actually. Pick a more fun alcohol, which I think came from the previous example. With HBr, this is a reaction from unit 7. You end up protonating the alcohol. This makes OH2 plus. This leaves to give you a secondary carbocation, which can then rearrange, give you a tertiary carbocation, which the Br minus that we ejected in a previous step can come in and react, and Br. Okay, so HBr does this reaction we looked at in unit 7, where we protonate the alcohol, it leaves because it becomes a good leaving group, makes a carbocation. If it's secondary, makes a carbocation, or tertiary. Primary, it doesn't. It does an SN2, like the example we just drew right here. And you get rearrangements. If you can make a chiral center, like let's say we have another carbon here, 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 still not a chiral center. We need another carbon. Now that's a chiral center. You're going to have 50-50 R and S. There's no preference to add one side or the other. The other option to convert an OH to a Br is to use PBr3. So if you have a molecule like this, what happens here is, I'm going to just redraw the PBr3. The OH does basically an SN2 on the PBr3. The hydrogen is still there, still has one lone pair. And that puts a positive charge on the OH. Plus there's a Br minus And then what this can do is SN2 that leaving group off. With inversion, right? Because it's an SN2. Okay, so why would you might want to use HBr versus PBr3? It's a primary alcohol or methyl or primary, both do the same thing. If you have a secondary, HBr can cause rearrangements. PBr3 will not. So PBr3 is the option to use there if you want to avoid a rearrangement. So I would approach this like you would have in Unit 7 with HBr. Is there a rearrangement? The answer is yes, and you don't want the rearrangement. PBr3 is the way to go. Like this example right here that we did above, HBr gives a rearrangement and PBr3 does not. Also, PBr3, I wrote that really weird. PBr3 causes inversion. HBr is not stereospecific. Meaning it doesn't do inversion, it doesn't do retention, it does a mix. You're going to get a mix of R and S if it's a chiral center. So that's another reason why you might want to choose PBr3 in that case. If you have stereochemistry that you want to preserve, PBr3 is the way to go. If you have a tertiary alcohol, only HBr will work. PBr3 doesn't work with tertiary alcohols, and that's because the mechanism I drew right here involves this SN2 step right here. SN2 doesn't happen at a tertiary center, so you can't have that displacement of the leaving group. So PBr3 won't do the trick here. So if it's tertiary, your only choice is HBr. If it's secondary, generally PBr3 is a better choice because it avoids rearrangements and preserves stereochemistry. It inverts stereochemistry. But HBr could be used for a secondary where neither of those are an issue, like the example we saw above, like this. And primary doesn't matter. Use them both. Either one. Both are okay. So that's for HBr versus PBr3 for alcohols. We still see Br2 in the use of light, water, heat, etc. So this one is a bit more involved. Doesn't HBr do a reaction similar to an SN2? It does a SN2 only if it's primary or methyl. If it's secondary or tertiary, it doesn't do SN2, it does SN1. Br2 in all of its glory. So Br2 does a number of things. In Unit 9, we did radical halogenation. And that's one thing that bromine will do. So if you have a starting molecule that only has CHs, like just an alkane like this one, what will happen is Br2 will do a substitution at one of these. It'll remove a CH and replace it with a CBr. But it's selective. It'll choose the hydrogen that has the highest degree of substitution. So if it can produce a tertiary alkyl bromide, it'll do that way faster. So for example, in this case, there's one tertiary center right there. Call that a methine, and there's just a CH there. This would be the major product. By that, I mean like 98% plus. If you have a case where you don't have a tertiary center like this, it'll still react, although it'll be slower. So if you had something like this, now we have a secondary site and a primary site. it'll preferentially react with the secondary site to give you Br as the major, plus it's an enantiomer, because I picked an example that has a chiral center. And again, this is going to be like 95% plus. So it'll react with secondaries if that's the best choice it has. And I guess it'll react with primaries too. The only example I can think of that has only, well, that's not the only example I can think of. I can think of a few. But if you have a molecule like this, okay, this has all of the CHs in this example are on methyls. This will be very slow. It will make a primary alkyl halide. It'll just be really slow. And the actual rates, the relative rate for attacking a primary carbon is 1. For attacking a secondary carbon is 80. So it's 80 times faster to go for a secondary, and it's 1,600 times faster to go for a tertiary. So that's where these major products that come from. They'll still do secondary, you'll still do primary. It's just become slower and slower. So that's Br2 when you have just an alkane. If you have Br2 with an alkene, like this, say, this will do an addition, reacts much more quickly with an alkene, which is anti. So this is a case where you can have different reactions using the same reagent depending on what you're reacting it with. And if you have a molecule with both things that can react with, you could potentially get both compounds. So by the way, up here, when we say bromination, when there's radical bromination, to do a radical bromination, you need an initiation step. And the initiation step makes radicals. And the initiation step in this example is Br, with that bond breaking homolytically to make 2 bromine radicals. So in order to do that, to do the initiation, you need some source of energy. So in this example, all these examples we have up here, we either use heat or light to do so. Heat is often abbreviated as a triangle, and the triangle means heat, and that's an ancient alchemical symbol. The ancient alchemists back in Roman times used triangles as the symbol for fire, and we keep that now in chemistry. That means heat. For light, we often use H nu. H nu is a Greek symbol. It's the Greek version of N, and this comes from where the energy of a photon is equal to Planck's constant times the frequency in seconds to the -1. So yeah, if you see these conditions with like H nu or light or heat actually written in there, that's necessary to do this radical halogenation reaction. We don't really need that in this case. Sometimes you see this reaction done, though, in a variety of solvents. So typical to do this reaction is a nonpolar solvent like hexanes or CCl4 are common ones that you see for this. But sometimes you see it done in a nucleophilic solvent, a solvent that can be a nucleophile. An example would be water. And what happens there is the Br still adds, but you end up on the other side putting an OH from the solvent. If instead you used Br2, and let's say you used an alcohol, ethanol, which is also a nucleophilic solvent, you can get an ether. So any kind of nucleophile here, and the mechanism for that is in the slides. If you want to see the mechanism for why this is the case, you can even do a reaction like this, where if you had that same alkene Br2, and let's say you used, I don't know, something like NaCl. You could, hypothetically at least, put a chlorine on there. Any nucleophile can potentially add on the second side of it there. Normally you don't see things like NaCl, but sometimes you do see that if you pick a solvent where you have very high concentrations, they can add for sure. I saw someone had their hand up there for a second, but I think it's down. Did someone have a question on this? Yes, go ahead, Sophia.
In the Module 9 practice assignment, in Terry's solutions, she did the same alkane plus the Br2 and light that you did up above, but in hers, she didn't show it as a chiral center. She just drew the Br as planar. Is that wrong?
Nope, that's fine. I mean, it's an opportunity where you can show that information, but if we didn't ask for it, then it's not wrong to not put it.
Okay, thank you.
Yeah, hopefully that makes sense. Yeah. Often though, when we do ask this, and this is just a general point for the exam, when we ask you to draw structures, I think on the exam in all cases say like explicitly show the stereochemistry. And what that means is use dashed and wedged bonds indicate if you have a chiral center, and if you get more than one product, please write them. It's best on the exam to err on the side of putting more information as opposed to less information. Going back to your original question, Elliot, I think that covers all instances of the use of HBr, PBr3, Br2, where we use light and heat, where we use water as a solvent or an alcohol as a solvent, as you see in this case. The only other things that maybe I didn't include would be the addition of HBr and Br2 to alkynes, which I can talk about as well. Less variation there, but we can certainly talk about that if you like. And I see another hand up. Yes, go ahead, Adriana.
You were talking about relative reactivity, like up above. Why is something that is more substituted more reactive?
Yes, because the mechanism looks like this. This is reacting with a bromine radical. And this produces a carbon-centered radical. So this is a tertiary carbon-centered radical. Tertiary is more stable than secondary, which is more stable than primary. So it's going to want to remove a hydrogen that produces the most possible stable intermediate. Because this thing is, it's high energy. If you can make something that's lower energy, that's going to be faster. And you can think about this if you look at like a potential energy diagram. And let's say your starting molecule is this energy, and we have to make a radical out of it. It's going to be a high energy to make a primary radical. If you're making a secondary, it's going to be more stable. And if you're making a tertiary radical, it's going to be more stable again. And what you notice here is that the height of the barrier, which is the activation energy, is smaller the more stable the intermediate is. So a small EA equals a fast reaction. So the fastest reaction will be the one that produces the most stable intermediate, where in a molecule like this one here, that's going to be the tertiary one. And the tertiary one is more stable because you have 3 alkyl groups, which are donating electron density to the central carbon, which is electron poor because it doesn't have a full octet. Cool. I see a bunch of support for Elliot's question, which says if there are no objections, going over alkynes too would be awesome. Great. Alkynes do essentially the same thing as alkenes, except they do it twice. This is my favorite alkyne for some reason. I don't know. Whenever I do examples, I always pick this one. If you use HBr, it will add HBr cross. In fact, I don't think it goes that way. I think this one, well, it'll react to give you the more stable alkene. You can add a second unit of it. This is kind of a bad example too. I'm gonna go back. I'm gonna backtrack a little bit just because I can show more information if I pick a different example. I'm gonna start with this alkyne. Then you can, there's differentiation now. This is Markovnikov. And you could add 2 units of it. The first unit reacts quickly. The second unit reacts more slowly. You can make molecules like this, which would be a geminal dibromide. Geminal means both of the attached bromines are on the same carbon. Okay. The other one is reaction with Br2. If we say like 1 equivalent, that means 1 Br2 for every 1 starting molecule you have. That will give you addition like that. If we said instead Br2 2 equivalents, then that will add twice like that. Give you a tetrabromo compound. Yeah, I think that's it. You might look at this and say, we added Br2, there's also a tertiary center. Can it do a, well, yes, if you had enough bromine in there and you left it long enough and you had light or heat, it could also brominate that one too. The bromine's all over this thing if you left it long enough and enough bromine, but generally speaking, we don't really ask you anything about those sorts of competitive reactions. If you see an alkyne, that's the reaction you want to do. Cool. Did I miss anything above that people want to see? Lizzie wants to see a ring addition problem, and I'm going to guess you mean a ring expansion problem. Yes, we're going to do a ring expansion. Okay, great. Let's do a ring expansion. Let's do this one. It's going to have an iodine here, and we're going to do ethanol, and we're going to do heat. So we have a secondary alkyl halide, ethanol, and heat. This all suggests E1. And what's going to happen is you're going to lose iodide. You have a cation here, which is secondary. Secondaries can rearrange. What I always recommend you do at this stage is to label all your carbons. I'm going to number them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Most common mistake here is for people to lose an atom. Don't lose any atoms. Make sure our product cation also has 10. What we're going to do is draw an arrow like this. So that means our carbon 1, carbon 10 bond is going to break. We're going to form a new carbon 2, carbon 10 bond. Okay. 1, 2, 3, 4, 5, 6. That ring is going to remain untouched. So I'm going to put the numbers in here. 1, 2, 3, 4, 5, 6. We're not touching any of those. We're not touching the 1,7 bond. So we can put the 1,7 bond here, but we are breaking the 110 and we're making a 210. So we can put the 210 bond in, and then we just connect the 7 up to the 10. So we have 7, we have 8 and 9. 7, 8, 9, 10. Now it looks like we added a carbon, but we didn't. If you count them up, we have 10 in each case. When we break the 110 bond, that means that carbon 1 is going to get a positive charge. Carbon 2 also still has the hydrogen that we had drawn in the previous step. Okay, now we have a tertiary carbocation, which is more stable. So there's a rearrangement there. Not only that, you get a bit of stability in this case by making another 6-carbon ring. 6 carbon rings have the least strain, so that's a good thing too. Lastly, we want to finish this off, and remember we said it was E1, so we need to take off the beta hydrogen at this time. There's 3 beta carbons. There's one here, and one here. The hydrogen that's already drawn is the best one. It's going to give the most stable alkene. So let's bring in our solvent here as our base. And it comes in like that. And that would give us as our product something that looks like this. So it's kind of funny looking, you know, like it looks like we somehow made it bigger or added something, but we didn't. Everything is still there. In fact, we removed stuff. If anything, all we did is remove things. We should have this, and count your carbons before and after to make sure you haven't lost any. Cool. Anything else you'd like to see? I remember from my email people asking about, from Olivia here, Newman and Fischer projections and ring flips. Newman projections. Let's start with Newman projections. Yeah, Victoria just put it in the chat too. Newman projections. Let's say I gave you a molecule like OH. And I say I want to see from you the Newman projection of this molecule looking down the C2-C3 bond. Okay, and if you label this molecule, we got 1, 2, 3, 4, 5. So C2-C3 bond is this one. So what that means is we're going to draw our Newman projection, which is a circle, which is the back carbon, which can be carbon 3, and a dot, which is going to be the front carbon, carbon 2. It's helpful to draw in the other groups on those carbons. Like that. So carbon 2 has 3 groups that are coming off of it, which are a hydrogen, an OH, and a methyl. In fact, I'm going to erase that one. I'm going to pretend my eye is here, looking at the molecule in that direction. That's going to be my forehead. That's going to be my nose. Okay, so that means if you're looking at the molecule from that perspective, the OH would appear on your right, the hydrogen would appear on your left, and the methyl would appear to be going down. So that's going to be your CH3. Off to the right is your OH, and off to the left is going to be the hydrogen atom that's there. If you mix up any of these two groups, if you switch the OH and the hydrogen, that would give you the opposite stereocenter. So this one is R. If you switch the OH and the hydrogen and the Newman, you're going to have the S. It's not what we want. Carbon 3 is the back one. Carbon 3 has 2 hydrogens, not a chiral center, so it doesn't matter which order we put these in. We have hydrogen, hydrogen, And then that other group, which is an isopropyl group, looks like this. So counting the carbon chain, we have 1, 2, 3, 4, 5. Would be like the longest straight chain here. So this would be the Newman projection for that particular compound. Often what we ask when we do Newman projection questions is to draw the most stable and least stable conformations. Generally speaking, the most stable conformation is the one that's staggered and has the biggest groups opposite each other. It might be a little bit debatable in this example whether OH or CH3 is bigger. Maybe CH3 is a bit bigger. But we don't ask you questions where it's debatable. We ask you ones where it's clear and obvious. So in this case, this may very well be the most stable conformation. The least stable is the one that's eclipsed and has the two biggest groups closest to each other. That maximizes torsional strain and van der Waals strain, which we don't want to do. Okay, from the 2008 exam, can you do 4B from the written? I will get to there, but first I'm going to do the Fischer. Lizzie wants the eclipsed, so if you want to draw the eclipsed, pick one of the carbons to remain fixed. I'm going to pick the front one to remain fixed, doesn't matter which one you do. And if you want to rotate the back carbon around 180 degrees, that will put T-butyl group there, hydrogen there, and a hydrogen there. That's the eclipsed one. That's the least stable one because the two biggest groups are closest to each other. Now Fischer. Chemists don't use Fischer diagrams very often, but it's used a lot in biochemistry, in particular carbohydrate chemistry. And because we eat sugars and build things out of sugars, carbohydrates like cellulose, we need to do those. So a Fischer projection is generally used when you have a molecule that has 2 or more chiral centers in a row, which is very common in sugars. So an example would be, if you have something like this, this is how we draw them, where the intersection points are chiral centers. Typically, we align the carbon chain to go up and down, and the side groups branch out left and right. And any group that is pointing left or right means it's coming towards you. Any group that's up or down is going back away from you. So to understand that, I often like to draw a picture of a cat. Okay, so if you have a cat, you can see how good of an artist I am here. They don't have straight legs like that. They have kind of bendy legs, but you know what I mean. Okay, and then they have and a nose. And then they have a tail that is usually up if they're happy. And they have another leg up front. Most of them do, at least. Okay, so this cat is a little bit shaped like a molecule. It has a group that's up, a group that's up. Right? Thank you, Michael. Where let's say we pick something like Cl and hydrogen, F, hydrogen, and methyl-methyl up there. That means this is a chiral center, and this is a chiral center. That means right here we have one of these, right? That's just a chiral center. Cat. Let's give him another one up here. Might look like something else, but that's not what I mean. Basically what we're doing then is imagine this cat is walking on a glass table. You are lying underneath that table and looking upwards. That what you would see looking underneath the cat is something that would look like this. You would see the body up and going away from you. You would see the head. You would see one leg pointing to the right. This is a bit exaggerated, Well, imagine you flatten the cat a bit. Going back and away from you, you would see the tail. You'd roughly see the cat looking like this. Chiral center, right? That's what I'm drawing up here. So what you want to do with this molecule on the right is imagine you're looking at it from the exact same perspective. You have to orient these two methyls so that they are eclipsed and draw what you see. So the top would be the CH3. You would have a fluorine to the left, a hydrogen to the right. On the bottom, you'd have a chlorine to the left and a hydrogen to the right. So those two are the same thing. And think of it like you are looking at the belly of a cat. That's basically what that should look like. Elliot, do you have any suggestions, tips, strategies for doing multi-steps? I sure do. Where we have the beginning product and the end product, but we don't know what's in between? Yeah, no problem. Are we okay with Fischers? We can come back to them later if people have more questions or want some examples or whatever. I have a feeling somebody emailed me a question on this today. Okay, here's one. This is a multi-step. I tell you what makes multi-step reactions easy is being super familiar with all the reaction choices that you know or that we've gone over. This is an example from some, I don't know, previous exam or something like that. Okay, so when I look at these reactions, I often think backwards. It's actually a strategy that won someone a Nobel Prize back in, I think, 1980. His name was E.J. Corey, who has also holds the record for most suicides in his research group. I think he has like 3 or 4 people committed suicide while working for him. So not something you really want to have, but there you go. So what do we have here? Look at the number of carbons. We have 1, 2, 3, 4, 5, and the product 1, 2, 3, 4, 5. Okay, that much is easy. So what we want to do is, okay, so this is a good one. So you can see that final product that has a bromine on carbon 5. Well, I guess it's technically carbon 1 if you name it properly. I usually start at the product and work backwards. Okay, so I think, you know, I would look at that and say that this probably came from that using HBr and peroxides. Okay, so I kind of work backwards from the end. That's called retrosynthetic analysis, which is the process which got that guy's Nobel Prize. And you want to then figure out a way to get from there to there. And it's awfully tempting to look at that and say, well, that's just a dehydration. Let's use sulfuric acid. But that's not good, because if you use sulfuric acid here, your major product is going to be this one. And that's not the one we want. We want it the other way around. So what we essentially want to do here is do a Hoffman elimination, and we don't have a reaction that's going to allow us to do a Hoffman elimination. We do Hoffman eliminations when you have alkyl halides using a bulky alkoxide. So that's not what we want. We don't want sulfuric acid. We want to turn it into something where we can do a Hoffman elimination. So I guess one thing we could do is just use like HBr. And that would give you this. And then we could do, it's kind of ugly looking there, but then we could do our Hoffman elimination. And this could give us a product going that way. So that's an example, nice example, I think, of a multi-step reaction that can get us there. Realizing the limitations of some of the reactions that we want, why we can't just shortcut our way this way with H2SO4. Even though it's tempting, don't do it. Always think for every step you write what the stereochemistry is going to be, and potentially what the what the regiochemistry is going to be too, meaning what constitutional isomer you're going to make. This example that we have right here, you're going to get a 50-50 mix of R and S because HBr is not stereospecific, but that doesn't matter for the next reaction, so we can throw away that chirality. Another way we could have done this well, we could have used PBr3 to do the same reaction. We also could have used something like trifle chloride with pyridine, PYR. And then done the Hoffman straight on that. That's OTF, by the way. When you have sulfonate esters like triflates, tosylates, and mesylates, they have chemistry very similar to an iodide or a bromide. Very good leaving group. They do all the same reactions that we looked at in Chapter 6 and Chapter 7 for alkyl halides. We sometimes call these things super halides because they're really good leaving groups. The other good thing about starting at the end for these multi-step reactions is oftentimes the end product you're trying to get, there's only one kind of reaction that'll make it. So let's give an example. Let's take I could give you a really nasty one. No, I'm not going to give you a really nasty one. Those are scary. How about that? That's an aldehyde. It's only one reaction we did that gives an aldehyde, and that is ozonolysis of an alkene. You could be that plus right? So that alkene, can we get from the alkene that's up there? Sure. It's kind of a bad example. I'm going to fix my bad example. So that's the alkene. We want to convert one alkene to the other. What we could do here is HBr and peroxides to give you this. This could be done using. So a common thing that you often see in these multi-step reactions is one alkene going to another alkene with different stereochemistry or different regiochemistry. So, you know, this overall transformation from one alkene to another alkene, basically like shifting the position of the double bond, that's achieved by doing an addition and then an elimination. And you can pick which side you add to, and you can pick which side you eliminate to by either using Zaitsever-Hoffman conditions or using Markovnikov or anti-Markovnikov conditions. So you can choose, you can sort of walk a double bond along a molecule if you want to make whatever it is that you need to make. Could you do one where you have to add carbons? Yep. I'm gonna do a long one. 4 to 5. How about that one? Well, there's really only one reaction that we did that adds carbons, and that's using alkynes, reacting the alkyne, a terminal alkyne with a strong base, the NaNH2, to make an anion, and then doing an SN2. So that's the only reaction we did. So at some point in this reaction, what we want is, you know, if we're going from 4 to 5, we probably want a 4 plus a CH3Br as one of our steps. Okay, so just move that down here. If we know that that's going to be one of our steps, then what can we do? Well, that is going to give us our 5, and we could go from here to here using H2 and platinum. Okay, so when we start breaking it down a little bit, you know, it gets easier. You know, it's manageable when you can kind of break it into smaller and easier to think about pieces. Well, at least now we have a 4-carbon chunk, and we're starting with a 4-carbon chunk. If you start with an alkane, there's only one reaction we did that begins with an alkane, and that's using chlorination or bromination, radical halogenation. So we could do this with, say, light. Right, we could do that. What else? We could do a Hoffmann to do this. We could add Br2, because there's only one reaction we know to make an alkyne, carbon-carbon triple bond, and that's using one of these with NaNH2 excess. Right? And so to make a dibromo like that, you need to start with an alkene. You can make an alkene by doing an elimination. You can make the alkyl bromide to the elimination by doing a radical halogenation. This is a lot of steps. 1, 2, 3, 4, 5, 6 steps. We don't ask you any that have this many steps, but this is a nice example of one that does have a lot of steps. If you can see and digest the harder examples, it might make the ones you come across a little more doable. But yeah, this is one where we add carbons. So if we wanted to make this easier, for example, we would just start you from here. Okay, like that's one thing we could do, or end here. We could cut off some of the early steps or late steps. But yeah, you could keep going and going and going with this. Yeah, you could make an arbitrarily long synthesis if you wanted to. Anybody else have something they'd like to see? I could pop into my email. I can see there's a few more questions I didn't get to yet. I see one from Rebecca, and it's asking a question that we did at the beginning of the tutorial. It's saying, it's coming back to this one again. We went through that just a little while ago and arrived at the best option being this, I think. And the question asks, why is this an addition rather than SN1? This is in fact an SN1, it's not an addition. Addition is when you start with an alkene and add something to it. If you are replacing something, like replacing an OH for a Br, it's a substitution. Let me see a question as well from Elizabeth. Hydroboration question, as well as how to protect an alcohol. If I have time, I do have time. And Lily says, can you review the difference between enantiomers, diastereomers, same molecules, and how to identify them? Yes, I can do all of these things. Alcohol protection and deprotection, great. All great topics. Let's do first things first. Hydroboration. So remember early in this tutorial, we went through all the variations of HBr and when you want to use HBr versus PBr3. What we can do is do the same thing for hydration. Hydration, we have 3 different sets of conditions where in some cases they all give the same product, this being 1. You could do 50% H2SO4. The other 50% is water. Sometimes that other 50% is written and sometimes it's not. If it's not there and you just see 50% H2SO4, assume the other half is water. You could also do the hydroboration oxidation. No. Yes, you can, but oxymercuration demercuration is what I'm thinking of. Mercuric acetate, OAC, is this. Acetate, just like you'd get from acetic acid. And this uses, I believe, NaBH4, sodium borohydride, in the presence of base. And in this example, that'll give you the same molecule all over again. Or you could use hydroboration, and the oxidation uses hydrogen peroxide. So hydroboration oxidation, they all 3 would have different circumstances when you'd want to use them. So the first one, which is sulfuric acid, the acid catalyzed hydration, this makes carbocations. So with carbocations, you get rearrangements sometimes, which is generally a negative thing. You can also, if you're making a chiral center, which you are in this case, you get like a 50-50. The addition of RNS, the addition is Markovnikov. And it's not syn and it's not anti. So we'd say it's not stereospecific. The other one, hydroboration oxidation, no carbocation, so there's no rearrangement. You still get 50-50 RS. You still get Markovnikov. And it's not syn or anti, just like, I guess, I mean, these 2 points are kind of the same thing. So the only difference between these 2 is the first one gives rearrangements and the second one does not. And the third option is the hydroboration oxidation, which is BH3THF, or sometimes you see B2H6 diglyme. These are the, as far as you're concerned, these are equivalent conditions. The hydroboration oxidation also gives no rearrangements. It gives you syn addition, and it gives you anti-Markovnikov addition. I'm just remembering going back when I did the HBr stuff. Did I do HBr in peroxides? It does anti-Markovnikov addition of HBr, if I forgot that before. In case I might have forgot that.
Yeah, I don't think you went over that, but...
Yeah. Sorry about that. It just popped into my head now. So yeah, if you have an alkene, this is a radical addition of HBr. This gives you this product. Okay, alcohol protection, deprotection. So alcohols react with a lot of things. They react with bases to make alkoxides. They react with acids to make carbocations typically. They react as nucleophiles. They react as, well, they can be oxidized and reduced. Those are reactions we didn't look at yet, but maybe in organic 2 you'll see some of those. So OHs do all kinds of things. So they're problematic. And so one thing that we often do to prevent OH groups from reacting is we protect them. We convert them to something unreactive, and then restore them back again. So an example I can give would be, let's say you have this anion and you want to do an SN2. And you want to do an SN2 like this to make a longer chain. Your problem with this is that the OH reacts with strong bases like this thing. And before it reacts by an SN2, it's going to instead react with the OH because acid-base reactions are typically faster. So one thing we can do here is deactivate the OH by protecting it and then restore it at the end if that's what we want to make. So let's say the molecule we want to make, 1, 2, 3, OH. If that's what we want to make, we can't just do it by adding these two together because the strong base will react with the OH first. So what we can do with the OH molecule is treat it with TBDMSCl. That stands for tertiary butyl. It's a tertiary butyl group. Dimethyl, oh no, the pencil's getting low. Dimethylsilyl chloride. And what that does is it converts our alcohol into an OTBDMS ether. It's called a silyl ether. And instead of an OH now, it has this silyl group that's on there, the silicon-based group. And what that does is it makes that OH no longer reactive. It can't act as an acid anymore. It doesn't act as a base anymore very easily. It can't be oxidized, can't be reduced. It's not a nucleophile anymore. All those reactions that OHs are well known for, it turns off those reactions. So now we can take this molecule, react it now with this thing. That'll do the SN2 because the OH isn't reactive. It's also not a good leaving group when it's on the T-butyl ether, silyl ether there. So that gives us our so that basically shuts off that part of the molecule. And then to get back to where we want, we can take the protecting group back off by adding fluoride. And TBAF is how we sometimes write it, which is tetrabutyl ammonium fluoride, which is nitrogen with 4 butyl groups, positive charge, and a fluoride counterion. Fluoride loves silicon. HF actually is used to dissolve and etch glass, which is silicon-based. So fluoride really loves to react with silicon, and that takes it off of the oxygen and gives you your alcohol back again. So sometimes we would call this BU4NF. These two are the same thing. Tetrabutyl ammonium fluoride, TBAF. That's alcohol protection and deprotection in a nutshell. We have another question up above by Lily we didn't get to. Difference between enantiomers, diastereomers, same molecules, how to identify them. So we always ask some questions like this, don't we? Enantiomers are mirror images. You have to have a chiral center for a molecule to be an enantiomer. Sometimes, you know, if we draw them in an obvious way, like this, if you can draw them in an obvious way where you can tell that they're mirror images and they have chiral centers, then, you know, you can identify them. Sometimes if they're not drawn that way, like here's an example. Let's say we give you this, then we draw the other one like that. You might look at that and say, well, doesn't look like a mirror image the way it is, but if I reorient it in a certain way, maybe it is. And what I think is easier than trying to reorient these, I mean, if you have a model kit, sure, build them and reorient them if you want. What I find easier is determine if it's R or S, the chiral center. They'll be enantiomers if the chiral center flips. They'll be the same molecule if the chiral center is the same. So I would look at this chlorine and label it R. The other one over here, notice the low priority group, which is the hydrogen, is pointing the wrong way. So the priority goes this way, which looks like R, but the hydrogen's pointing in the wrong way, so it's actually S. So they look like the same molecule, but they have opposite stereocenters, so these are going to be enantiomers. Diastereomers are typically molecules that come in cis-trans pairs. So the easiest example to see would be something like this. Right? One's cis, one's trans. These would be diastereomers. Another easy one to see is if you have like a dialkyl cyclohexane or something like that. You know, we could say that these two are cis, these are trans. The hardest ones to see, though, in my opinion, are ones that are on like an open chain. Something like that. What you can do in this case is, again, check all the chiral centers to see if they're R or S. This one's R, this one is S. On the right-hand side, still S, and this is S. They'll be enantiomers if every chiral center flips. They'll be diastereomers if some flip, but not all of them flip. So in this example, one of them flips and the other one does not. That means these two molecules will be diastereomers. Although this molecule those two are enantiomers. Same, of course, as if all the chiral centers are the same and otherwise the connectivity is all the same. Constitutional isomers is if they, you know, if there's bonds in different places, like this versus that. You know, it's either between 1 and 2 or between 2 and 3. These would be constitutional. I think those are the only conditions, though, where you see diastereomers or enantiomers. Diastereomers, easy to see in alkenes or dialkyl cyclocompounds, but this is probably the more tricky one, where you have multiple chiral centers and they're not fixed in a chain, in a ring. But yeah, if you can remember that, if all chiral centers invert, they're enantiomers. If some do and some don't, they are diastereomers. Michael Alder asks, can you go over a Williamson ether synthesis reaction? Yes. Williamson ether synthesis is the reaction between an alkoxide and a primary alkyl halide, which is an example of one of the reactions from chapter 6. So if you have this plus Br primary alkyl halide and an alkoxide, these will do SN2s. 1, 2, 3, O, and then it'll put 3 carbons on the other side as well. This has to be primary or methyl, because if it's not primary or methyl, the reaction you get instead is an elimination, right? If you tried to do this reaction it's not going to give you an SN2 as the major root. It's going to give you an E2 as the major root. And this is something you would have remembered back from chapter 6. We're not changing any rules here. So secondaries don't really work. Tertiaries, for the same reason, also don't work. You don't have a chance of getting an SN2 with a tertiary. Alkoxides can be a bit problematic too. Like if you use a secondary alkoxide, we never really talked about secondary alkoxides in chapter 2, and that's because we either wanted the Hoffman elimination or Zaitsev. So Zaitsev, you use a primary alkoxide. Hoffman, you use a tertiary. You use secondary, you're going to get a mix. So we don't like mixtures generally. We just want one thing, so we avoid secondaries. If you have a secondary alkoxide, though, and a primary alkyl halide, the major product will be substitution, SN2. But if you have a tertiary alkoxide, even with primary, major is E2. So Williamson ether synthesis is a little bit limited in that it works great if both are primary, like you see here. It works okay if the alkyl halide is primary and the alkoxide is secondary. Any higher than that, and it doesn't work at all. You get elimination as the major product. This is a major problem with this particular reaction. Unless, for example, you have a reaction where elimination is not possible, then it can work great. So if you have an alkoxide like this, and let's say you have a benzyl, which I think you might have done this one in the lab. In this case, you can do an SN2 no problem because there's an alpha, but the beta carbon down here doesn't have any hydrogens, so you can't do elimination on this one. So in this case, now we didn't really use many examples with phenyl, and there's none on the exam either. So you don't have to worry about it, but just so you know, Williamson ether synthesis becomes more useful. There's a wider variety of reactions you can do when you move away from just straight alkyl chains. Lord says, is there another possible answer for the Fischer projection you drew? It's going a ways back, isn't it? Fischer projection, how far back was that? Yes, Fischer projection. So with Fischer projections, you can do a rotation of 180. So the other way of drawing that correctly is to flip it around. So you have Cl up here and F up there. So basically, it's like you picked your page up and looked at it upside down. You flipped your page around 180. That's another way you can go about doing these for sure. Great. Covering a little bit of everything today. I think that's all the questions that got emailed to me. But I'm happy to take any other questions you have. You want more multi-steps?
Yes, please.
Okay, I got to come up with these on the fly. That's the problem with these. Just more straightforward one. Don't fall into a trap either. Sometimes textbooks call them synthesis traps, where it's like there's a reaction that looks like it's going to work well, but like think these things through. So here is my example. Br So many people will look at this and it's like, oh, all we're doing is we're adding a Br. Let's just use Br2 in light and be done with it. And you might make a little bit of that, but you're going to make a whole bunch of other things too, right? Like that bromination can go anywhere in this molecule. There's hydrogens all over the place. This is a really bad way to make this particular molecule. So let's not do it the bad way. Let's look at it and say, oh my God, look, that's a vicinal dibromide with anti-addition symmetry, right? Like that product should scream at you, I want to be started from cyclohexene and react it with Br2 with some nonpolar solvent like hexanes. Okay. And can we make that from that? Yeah, easy peasy, right? Any elimination conditions will give you that. There's no Zaitsev to worry about, no Hoffman, none of that. Let's just use any alkoxide you want, and that'll do that elimination. It's a two-step, and it'll make that product right there. So these are a little bit easier to handle, maybe. Like that previous one I gave you with like 7 steps. Yeah, okay. We're not going to give you ones like that, but okay, look at that. CN. Where do you see CN? We see CN as a nucleophile, a very strong nucleophile, loves to do SN2s and things like that. But looking at it, people realize you can't do an SN2 directly on an OH. Okay, I'll give you the possible reactions students think of when they see a question like this and rank them from worst to almost worst to correct. A lot of people would look at that and say, okay, look, HCN. Actually, that's not the worst one. That's not the worst one. The worst one here would be if you said NaCN with some solvent. Because to do an NaCN, you're asking this to do an SN2 or maybe an SN1, but you're asking OH to leave, and OH is not going to leave. So that's not going to work in one step. HCN you might think is a better example because, well, at least then you can protonate the alcohol and you know, make it a good leaving group. But first of all, HCN isn't something you've seen in the course. So, you know, advice number 1, don't use reagents you never saw in the course. HCN has all kinds of problems with it. It killed Lewis, actually. The guy that came up with Lewis structures died because he inhaled HCN, but toxicity aside. If you want this to do an SN2, the stereochemistry is wrong, right? So I look at this and say, well, maybe we can do an SN2, give it a good, nice SN2 solvent, something polar aprotic, maybe DMSO. And, you know, if you had something that was like that, then you're doing okay, right? Can we do this? Well, it just so happens we have a perfectly great reagent that will convert an OH to a bromide and invert the stereochemistry. PBr3. Beauty. How about something like this? SH, the sulfide. When do you see these? Well, you see these when you do SN2s. Could you use HBr instead of PBr3? The answer to that is no. Because if you used HBr instead of PBr3, you're going to get not inversion, you're going to get a 50-50 mix. You're going to get that plus the enantiomer. And then when you get to this step, you're going to get that and the enantiomer. So that would be an example of, like, you know, let's say this question was worth 5 points and you put HBr instead of PBr3. You wouldn't get full points, but you would have still made the product, right? You just didn't use the best conditions because you lost your stereochem. So I don't know what that would be worth, 3 or 4 out of 5, probably. Because yeah, you would get the enantiomer as well because HBr addition is not stereospecific. Okay, my pencil's complaining, so I've put my pencil in my phone. It's going to be really awkward to write with, but give myself a little bit of juice. Okay, another piece of advice for these multi-steps is if we say give a multi-step reaction to do this transformation, only make sure there's more than one step. We don't give you ones where you can do it all in one step. So if you have an idea that you think you can do it in one step, you're probably wrong. So think harder, think a little bit, consider the stereochem. You know, this one I just wrote down here is very tempting to give NaSH and I don't know, DMF or some other Polaroid product. Try to do an SN2, but that gives you the wrong stereochemistry in this case, right? Because SN2s invert. If we try to do an SN2, we didn't get the inversion here, so that's not going to work, at least not all at once. So this is an example where maybe we could do 2 SN2s in a row. What if we used NABR F did an SN2 and inverted it, then we do something like that. That'd be smart, wouldn't it? Yeah, there's ways of doing reactions like this. Because you might look at that first one and say, okay, the product of the first SN2 is I minus. Can't that just come back in again? It's like, yeah. So sometimes there's experimental considerations which you have to consider, like things like that, where you might add something that grabs the I minus and prevents that second reaction from happening. But you don't have to worry about that for the exam. Yeah. Cool. That makes sense. So things to worry about for these, consider for these multi-steps are when you have chiral centers, being sure not to throw away your stereochemistry. You want to use SN2s when you can because they do inversions. They don't lose your stereochemistry. When you're moving double bonds, think about addition, elimination, combinations to move double bonds around the molecule where you want them to go. Because you can pick directions using Hoffmann or Zaitsev conditions. And when you're doing additions, you can pick Markovnikov or anti-Markovnikov. If you start with an alkane, the only reaction you can do is bromination or chlorination. Almost always the correct answer is bromination and not chlorination, because chlorinations are not very selective. Brominations are, so they're typically a better choice. The only example where chlorination is a good choice would be if your alkane is such that all CH positions are equivalent. And in that case, you could use bromine anyway. Right? So that'd be fine in a case like this, but in a case like that, Cl2 is no good because you'd get Cls all over the place here. Anything else people would like? Out of curiosity, do you know what reaction is most prevalent in human physiology? SN2s all over the place. And you'll learn about that when you go into biochem. There's all kinds of SN2s taking place inside enzymes. Also water, right? It's all over the body. It's a nucleophile. It can do SN2s. Actually, it's probably not the most prevalent. I'd say acid-base reactions are more prevalent than any kinds of substitutions. Acid-base is super, super common in biology. There's lots of cool, funky ones too, though. Like a super complicated reaction is photosynthesis, because it takes place, like it's photochemical. There's a transport of electrons and protons across membranes involved. It's like a very, very complex type of reaction. What kind of reaction would beta oxidation be, for example? Oxidation reactions, yeah, like generally you'd call an oxidation like an electron transfer reaction. There's lots of those in physiology as well. Yeah. Wait till you get to biochem. You get to learn all about these. Victoria, how do people usually do on the exam? Do they usually do better than midterms? I'm going to draw you a graph. Performance. Midterm 1, midterm 2, exam. Most years, it goes like this. In terms of class average, okay? Midterm 1 usually has a higher average than midterm 2, and the exam is somewhere halfway between-ish. What I've noticed is people who, let's say, are above average on midterm 1 typically do better on midterm 2 and either the same or better again on the exam. That's what I find. People who are in the middle typically do bad on midterm 2 and recover a bit. Some people recover a lot. I've seen huge jumps from midterm 2 to the exam. That's usually people who didn't have time to study for midterm 2 and pull it together. Some people, it all depends, right? Like if you had a big drop from midterm 1 to midterm 2 and you did nothing in the in-between time to correct that, usually there's another drop for the final exam. And I think that's because the first midterm has enough stuff from first year in high school, like Lewis structures, molecular shapes, all that kind of stuff, that you can collect points. And I'd say there's less and less emphasis on that sort of thing going into the final exam. More emphasis on the reactions and mechanisms and stuff that we did new in this course. Out of curiosity, where does the exam average normally sit? This is going to be an unusual year because our midterm 2 average was dramatically higher than it normally sits. I'd say midterm 1 average is normally around 70, 71. Midterm 2 average is normally around 60. And the exam is, I'd say, high 60s. But this year's midterm 2 average was like 80. And that's because you guys are an exceptionally intelligent year, right? Nothing to do with open book. Although averages I find a bad measure because some people do very badly. Like some people will get, this is the kind of course that it's hard to bullshit your way to a 50. If you don't know 50% of the material, you're not going to get a 50. And so like, if the average was say a 75, a 25%, if someone gets a 25, that'll bring the average down a lot more than somebody getting 100 would bring it up, right? You'd need 2 people to get 100 to undo 1 person getting a 25 to maintain your average at 75. Did I do the math there right? So probably a better measure is median. I still say for most people, their midterm 2 average is their lowest grade out of all course components. Because the other thing that happens at the end of the year is we factor in your assignments and we factor in your lab marks, which it certainly brings the average up. People who really get the material and study hard and know it well often do very well on the second midterm and the exam. Often better than midterm 1 because there's less, I would say, picky details. Like There's lots you can go wrong on easy on midterm 1, where I find towards the final exam, it's more, if you get it, you can get 100% on a question, right? I don't know if that's helpful at all. It's hard for me to say for sure, but you know, certainly the exam is quite doable. I don't think it's going to be too much of a surprise, especially the fact that this year you have open book that makes it a lot easier not to miss little points on like getting your conditions wrong and stuff like that. Hi, Percy. I'll do my demonstration of the Percy wanted to help with the Fischer projections. He doesn't want to sit down. Okay, question 7 of the written in 2019. I forgot what I was doing. Written 2019. Will it be harder than other years because it is open book? I think it's pretty comparable. Here's my feeling with this exam. I find the multiple choice section is easier than last year's multiple choice, and the written part is harder than last year's written. And not even harder, it's just, there's nothing too unusual on there. Maybe it's just, you know, I would say that it's not even true. I was going to say, like, there's not as many questions that you can't just like look up in your notes, but I don't even think that's true. I think there's, you can look up a lot of this stuff in your notes. Don't look it up on Google. Question 7. Okay, do you want all parts? Question 7 of the written portion, please. Yeah, let's do question 7, 2019. This is a multi-step. This is a great example where people would love to do this in one step. People very much would love just to say Br2 and light. And say, okay, that's our product. We add bromine, we're done. We're off to the races. No, because that's not what you're going to get. You're going to get this. Because bromine is selective. You're going to get a 50-50 mix of R and S, which we also say is racemic. If we had this alkene, we could do HBr and peroxides. And how are we going to get that alkene? That's going to be just a Hoffman elimination. I feel like we've seen ones like similar to this. And that's what I find, like, practicing these is super valuable because, like, we're not as creative as we'd like to be. So similar types of patterns come up. Oh, you guys got choice last year. That's one thing maybe that makes this year's harder is there's no choice. And the reason we're anti-choice this time is with Gradescope, it's super difficult to grade them when there's choice because it does it one question at a time. Okay, multi-step to, oh, get away. This, and again, there's only one reaction we know of that makes alkynes. if you don't start with an alkyne and you end up with one, think of a compound like this. Three equivalents. You need to do an acid workup here. Because if without the acid workup, what you're going to get is this. So you need the acid workup to install that hydrogen back on in the end. So this condition, this reaction, that's how you make alkynes. That's the only reaction we know of in this course that makes a carbon-carbon triple bond. And then this part is pretty straightforward. This is, yeah, you already told me that. This is just addition of Br2. And you wouldn't use water, you wouldn't use alcohol, you'd use a non-nucleophilic solvent like, I don't know, CCl4, carbon tet. Although nowadays you wouldn't use that because that destroys the ozone layer. You'd use hexane or hexanes. Sometimes you see plural hexanes. It just means it's a variety of hexane isomers, not just straight normal hexane. You could have branched isomers. Doesn't matter. Doesn't change its chemistry. It doesn't do anything there. The only purpose of the solvent in this case is to make sure everything's all together in one phase. And that was it for the question. There's only two questions there, only two parts.
So is it for every equivalent, it adds like an extra bond?
That's true for the first two. So I can go through that mechanism if you like. Because we have a hydrogen here, and a hydrogen here. Can the NaNH2 only be used when you go to the alkyne? You can use NaNH2 anywhere as a base. It's a bit of like using a sledgehammer to drive a finish nail in. It's a very, very, very strong base. You need a base that's that strong to do this. If you want to do like an E2, yeah, it'll do an E2, but alkoxides are a little more mild. So that might be a better choice. NH2, super strong. So it's going to do an E2 in this case. I honestly don't know which bromine gets knocked off first, whether it does this or takes or eliminates the other way first. Doesn't really matter though. Well, it matters, but it doesn't matter for us. So this next one is kind of weird because this is the one that's hard to do. The first one is an easy peasy, like that's like an elimination that you would have done at any point in time. This next one, not so much. And so that's equivalent number 1. This is equivalent number 2. Then equivalent number 3 comes in and deprotonates. That's where the 3 equivalents come in. You only need the third equivalent if it's a terminal alkyne. And you might say, well, why don't you just add 2 equivalents and have it stop there and not take off that last CH? Problem is acid-base reactions are fast. So once you do the first 2 eliminations, the third one happens immediately. So what would happen if you added 2 equivalents is you would get this and you'd get a 66% yield. And then you'd have 33% starting material. So that's why you have to add all 3 equivalents. If you want to push all of it to that, if you want 100%, you need 3 equivalents, and then you add a source of protons. Water is enough, actually. And you put the hydrogen back on. We sometimes just call this acidic workup, something that can put a H+ back on your molecule, like water. Julia, will the multiple choice look more like the 2019, where it's a mix of everything, or look more like the 2017? No, it's more like the 2019. In fact, I can tell you exactly. The first 20 questions are all material. First 19 questions, it's out of the 60, is all material up to the first written midterm, not counting the oral one. The next 20 questions are all material from chapters 6 and 7, 5, 6, and 7, material that was on the last midterm. And the last, I think it's 21 questions, are a mix of material since the last midterm, which would be units 8, 9, 10, and a couple of like reaction questions that blend together a couple of different chapters. So yeah, I would say that the multiple choice is more like last year's multiple choice, more like the midterms that you saw this year, easier than the 2017. 2017 was pretty tough, some of those. There was lots of like multi-steps, lots of like, yeah. Good questions, great practice. If you can do all the 2017 ones and answer them well and understand why they are the way they are, you'll be in really good shape for this final exam. Yeah. The other thing that people are usually bad at is resonance, right? We do it right at the beginning and we kind of don't talk about it, but just remember that resonance is still important. And if you have like a cation, carbocation, for example, you can have resonance structures which look like this. And what that means is the charge is shared over the two atoms. And like even if you had a reaction like this and you had, let's say, a nucleophile attacking, it could attack either one, to be honest, because there's positive charge at both of those. We didn't really talk about these, and we'll do a little bit more of them, but yeah, it's a nice addition of the concept of resonance to, in this case at least, reactivity. Anything else you'd like to see? I think our scheduled time is till 3. I can go for about another 10 minutes.
Could you go over a resonance structure example?
Sure. I had written down that it was until 2. It was down until 2 on Acorn. I made it longer. And yeah, I'm just so giving with my time, aren't I? Resonance structures. Let's go. There's two kinds, kind of. There's the cation and anion ones. My observation is people are way better with the cation ones for some reason. You know, if you have an atom like this, sometimes it's helpful if you draw the hydrogens in too. So what you're looking for when you have a cation is a pair of electrons on an adjacent atom that you can move over. And that pair of electrons can either be in the form of a multiple bond or in the form of a lone pair. Let's get the lone pair example out here too. Okay, so in this case, you could look at the atom next to it on the right and say that's a saturated carbon, meaning it's got all single bonds, no lone pairs, no double bonds. There's no way you can push the electron, the positive charge in that direction. There's no electrons you can bring down to get rid of the positive charge where it is. But on the other side, you can see there is a double bond here that we can move over. Remember to use the right arrows. That would put the double bond here, put the charge here. Okay, still a hydrogen there. And next we could look around for that one to see if we can do this again. If you look where you came from back up here, there's a double bond there, but if you bring those electrons down to the positive charge, you're just going to go back to the left. But if you look on the other side, we can take that pair. And if you do that, you will have a positive charge here. And finally, if you look, keep going down, the nitrogen has a lone pair on it. You could move the lone pair down as well. And you could have something like this. So this carbocation has 4 resonance structures. You can connect those two if you want. This would be a really stable carbocation. I mean, it would still react with nucleophiles, and you couldn't buy a bottle of this stuff. But compared to all the carbocations we've seen in this course, this one would be way more stable. One question we often ask is which is the major resonance contributor, which is the most stable. I mean, I don't like saying which one of these is most stable because it implies that they're all different molecules. These are all different ways of drawing the exact same molecule. But the biggest contributor would be this last one, and that's because it gives every atom a full octet. So that one's not so bad. The bad ones are the anion ones. This is a phenolate. This is something you'd get if you added a base to a phenol. And phenolates are easy to form because they are resonance stabilized. So here we have a negative charge. When you have a negative charge, what we're doing is we're pushing electrons somewhere else. So we have any one of these electron pairs, we're going to push down into the adjacent bond to make a double bond there. We still have 2 pairs left, but we have to move something else because you can't have a situation like that because that would have 5 bonds to that carbon. So if you push electrons down to that carbon, we have to push the electrons that are there somewhere else, like there, for example. And if you do that, there's a hydrogen here to begin with. We now have a pair of electrons there, a negative charge, and you have this structure. And just like before, we can continue to push these electrons around, push them down to the adjacent CC bond, and if you push them there, you're going to have to take the electrons that are already at that carbon and push them away too, because again, you can't have 5 bonds to that carbon. Don't feel too bad if you find this difficult. We had a faculty candidate a number of years ago who interviewed and tried to draw resonance structures of this exact molecule and did it all wrong and then got confused. And then that was during their interview. They were giving a talk to students about what they were working on. So even professionals get this wrong sometimes. So this is another one, and we can do it one more time. You can have that. So what this means is the overall molecule is going to be a blend of all of these structures, not necessarily an equal blend. Some of these will be bigger contributors than others. The biggest contributor in this case is the first structure because it has the charge on an electronegative atom. And for another reason, which we'll learn in organic 2, called aromaticity, but it means the real structure might be like negative 0.5, negative 0.15, negative 0.15, negative 0.15. Like that negative charge, let's put a 5 there to make them all add up. That charge is going to be split on a number of sites all over this molecule, which is weird to think about because we're sort of trained at this point to think about electrons as little like dots that got to be in a place, but they are not. They can be blended. They can be delocalized is the word we use. Is it true that if you do better on the final, then on your lowest midterm, the lowest midterm mark is dropped? Yes, that is definitely the case. We are dropping the lowest midterm. Whichever one of the 3 is your lower mark, we will drop it and replace it with your final. That is only if you do better on the final. We wouldn't drop a midterm if it lowers your grade. Right, so yeah, if all of your midterms were 70s and your final's a 90, then we'll throw away one of your midterms. But if it's the other way around, we won't. Yeah. What we do is we calculate it both ways and just give you whichever grade's higher. Also, it's easier this year to get A+ now because they changed the grading scale. I'm not going to say you just need a 90. It used to be you needed a 94. But if we express the average of the course in terms of a GPA rather than a percentage, the GPA of the class will go up this year just because we're now on the new scale. Yeah. So yeah, we do match up with other universities better, which is great if you, I don't know, if you're applying to a competitive program like medicine or something, and if they use your GPA as an important measure. Medicine might be a bad example because I think they look more at MCATs, but yeah. Now, if you're at the top end, yeah, it's going to be easier to get an A+. And an A+ is worth more. It's worth 4.3 now instead of 4.0. Let's see if we can get everyone into a A+ in this course. That'd be great. All right, I told you folks that I had to go in 10 minutes, and it's now 11 minutes, and I do have to go. My wife broke her foot, so I have to pick her up from work. She can't drive. So it's been a pleasure. If you have more questions for me, you can email me, and I'll do my best with them. And I, at some point before the end of the day, will post this up on Acorn. So if you need to see any parts of it again, you're welcome to do that. Awesome. Thanks everyone for coming and asking lots of nice, thoughtful questions and bringing up the dirtiest examples we gave over the previous years. And get a lot of sleep. All right. See you everyone. Happy holidays. Merry Christmas.